Stephen Hawking and the Science of Black Holes. If you're curious about space research, so subscribe to your channel and comment below, and if you are from America, so you know Area 51, coming soon. He was the last physicist whose unique profile transcended the boundaries of science to become, like Einstein, an icon of popular culture. His image has remained linked to the field that accounted for the bulk of his work, black holes. The discoveries of Stephen Hawking, the 8th of January, 1942 to the 14th of April, 2018, shone light on the darkness of these mysterious astronomical objects, but at the same time raised questions that will continue to trouble scientists for decades to come. In the mind of the public, black holes are often imagined as huge cosmic vacuum cleaners that suck up everything in their path, including light. This is an evocative but incorrect idea. A black hole is not and does not create a vacuum, but quite the opposite, it attracts through the effect of gravity, because the density of its mass is so enormous. It follows that we should have nothing to fear if the Sun were to be replaced by a black hole of the same mass. Though our world would be much colder and darker, the planets would continue to orbit undisturbed because the mass of the black hole would be equivalent to that of the Sun. The existence of black holes stems from the theory of general relativity published by Albert Einstein in 1915, and the subsequent work of Robert Oppenheimer, Karl Schwarzschild, Subrahmanyan Chandrasekhar, and others. Space and time form a fabric that is curved by mass, like a trampoline. A black hole is a ball so heavy that it has at its center a singularity, a region so infinitely dense that it collapses the bottomless trampoline. Any object we place nearby will tend to fall towards the ball, so the gravitational effect of the black hole is felt in its surroundings. Astrophysicists have been able to identify many such black holes by discovering cosmic objects orbiting around an apparent nothingness. This gravitational pull reveals the presence of something that is otherwise completely invisible. These black holes are often called stellar black holes. They originate after the death of a star whose internal gas pressure pushing outwards can no longer counteract the enormous force of gravity, which compresses its remaining matter until it collapses into a black hole a couple of dozen times the mass of the Sun. These are tiny compared to those that can store up to millions of solar masses, the supermassive ones that sit at the center of many galaxies. At the other extreme, there are black holes even tinier than the stellar ones, micro-black holes formed in the early universe. Regardless of their size, they are all surrounded by an invisible boundary called the event horizon, the point of no return beyond which nothing can escape, not even light. Around that horizon, the masses of dust and gas are so accelerated by the gigantic influx of gravity that they heat up and glow, emitting radiation and sometimes forming an accretion disk, which allows us to observe the shadow that the black hole itself casts on the luminous ring. Thanks to this effect, the Event Horizon Telescope, EHT, an international collaboration of ground-based radio telescopes, succeeded on the 10th of April, 2019 in providing humanity with the first image of a black hole, which occupies the center of Galaxy M87. As Hawking would explain in the public version of his theory, formerly incorrect for the sake of easier comprehension, as physicist Ethan Siegel explained, quantum theory suggests the continuous creation of virtual particle-antiparticle pairs that annihilate each other almost instantly. But if this happens right at the edge of a black hole's event horizon, it may result in the negatively energetic antiparticle falling inwards, stealing energy from the black hole, and its partner escaping into space with identical positive energy. Eventually, this would lead to the total evaporation of the black hole with no matter or energy escaping from it, although, as Hawking pointed out in his study, for a black hole of solar mass this is much longer than the age of the universe. In much smaller black holes it would be faster, culminating in a final explosion equivalent to 1,000,001 mton hydrogen bombs, he wrote. Hawking radiation. Hawking's d.